think that works fine. Then I'm just left to my whiteboard marker sheet. Finish loading. It is taking a little bit of time. Okay, let me just start from that other whiteboard marker for this one stops. So if I have a function, so if I have a function y, say equals to f of x, I have a function y is equals to f of x. Now my aim is that okay, we know that obviously that dy dx is going to give me something like what we called, say, f prime of x. Now if I keep differentiating this, so if I differentiate this, let me call this 1. Let me call this 1. Let me call this 2. Now if I should differentiate this again, I'm going to have what we call d, it means d dx of dy dx.
Yeah.
Equals d dx of f prime of x. Now, obviously, this is going to give us d square y, d square y over dx squared. Then this is going to give me f prime of x, that is second derivative of f with respect to x. Now, if I should continue to the nth derivative, then I'm going to have something like the ny. N is going to be a positive integer over the x squared. This is the xn. No, sorry, don't mind. The xn equals, I'm going to write fn of x. Guys, I disturbed my class. So this is one achieve. Can we generalize the derivative of a particular function to the nth term? So that's the challenge. So hold on. Hello, so
Hello.
so now it's just find the general term for the derivative of this function. Now, so that's the challenge. So it's just like find the first derivative, find the second derivative, find the third. Then from the pattern you can see some pattern, then you just have to generalize. Okay, so let's take for example, let me have a case study here. Let me the case studies, 1 or 2 case studies. So I have x is power 4 in x, for example. So I have x is power 4 in x. There's what we call can you remind me? I've forgotten that function, that rule to use to find the general term of a product function. Leibniz formula. Yes, I can remember. Leibniz formula. So along the line, might need Leibniz formula for some cases. So, but then, so let's start from two basic points. Right? We are not necessarily going to need Leibniz formula in this case. So let's say, so I'll take ln x as a case study, first case study. So let's say y is equal to ln x. We want to find the general term to do that. So y is equal to ln x. Yeah. So what is the first derivative? dy dx is what? What's dy dx? Ln x. This is 1 by x. Good. Good. So let me put a comma. So now what's the second derivative? That is, if I differentiate this again, what do you think I'm going to get? What will be the second derivative of this? You said?
1.
Minus 1 over s squared.
Okay.
Is that not what I'm supposed to get? Is that not what I'm supposed to get? Yeah?
Yeah.
Do you understand?
Wait, the differentiate what?
If I should differentiate 1 over x, isn't
Mhm.
this what I'm going to get? Do you understand how I got this?
Explain.
Okay, so now, if you want to differentiate, say, x is per n, for example, how do you differentiate this? That will be the power, I mean, times x
And X,
is
X
for the
minus.
power what? Minus 1. Good, right?
Yeah.
Now, 1 over x now, do you agree that it's the same thing as x is per minus 1? Do you agree?
Yeah.
So minus 1 times x is what? Minus x, right?
Yeah.
Minus 1 minus 1 minus 2.
So,
So this is now minus x is per minus 2 is 1 over x squared.
okay, thank you.
So that's why we have the second derivative of this will be minus 1 over x squared. Alright, so let me erase this now. And so our second derivative is let me just put it there, square y over the x squared is minus 1 over x squared. Now the next in line is that, okay, once I find the third derivative. Now the third derivative is the cube y over the x cube. Oh, this is going to give us, this is going to give us 2 over x is power 3. If you do your maths, you understand that this is actually this, because this is minus x is power minus 2. So minus 2 times minus x, that's 2x is power minus 2 minus 1, that's minus 3. So you have this. Do you understand?
Yes. Yes.
Now, if I should go further to do for the fourth derivative also, I should have something like minus 6
Yes.
over x is power 4. Do you agree? Yeah.
Yes.
If I also go further to find the fifth derivative, I should have uh, 24 all over x is power 5. I can go on to differentiating this further, but it won't help me because I want to get a particular generalization, which is dny over the xn for any positive integer n. This is where I'm going to, but just continue this process won't really help me. But can I find a pattern? Now the pattern I can find here is that if you notice, when the derivative at odd numbers are positive, while at even numbers they are negative. So if I see d1 y dx positive, for third derivative positive, for fifth positive, for the evens you have it to be negative. Now there's a pattern. It means first of all your signs are fluctuating. So I can say this is equals to -1 is power something because of that fluctuating pattern. So this -1 is power, say, so -1 is power 0 is 1, abi, right?
Yes.
So I can start from, okay, this is 0. Now this is going to be equal to, I can say this one is -1 is power 1, because as I'll be increasing the number as the derivative increases. Now this is -1 is power 2, because that's going to be positive. This will be -1 is power 3. Which is negative. I can continue that this was also -1 is power 4, which is positive. So I have a pattern. So for the first derivative, I will have -1 is power 1 minus 1, which is 0. This time I will have -1 is power 2 minus 1, which is what?
Yes.
I have -1 is power 3 minus 2. 4, so what am I saying? 2 minus 1, 3 minus 1, 4 minus 1, 5 minus 1, right? I'm using the
Yes.
pattern of the derivative because this is power 1, 1 minus 1, power 2, 2 minus 1, power 3, 3 minus 1, power 4, 4 minus 1, which is 3. So it means this one has to be what? -1 is power n minus 1, right?
Yes.
Good. Now, another problem we have is that the numerators. Now, for the numerator here I have 1. For the numerator here I have 1. But for this one I have 2. This one I have 6. This one I have 24. But there's still a pattern. And the pattern is that this is a factorial pattern. Because 1 is the same as 0 factorial. 1 is the same as 1 factorial. 2 is the same as 2 factorial. 6 is the same as 3 factorial. 24 is the same as 4 factorial. Are you getting it? So now look at this. This is like 1 minus 1 factorial, 2 minus 1 factorial, 3 minus 1 factorial, 4 minus 1 factorial. That's at the fourth derivative. At the fifth derivative, I have 5 minus 1 factorial. It means that at the nth derivative, I'm going to have n minus 1 factorial. Does that make sense?
Yes.
So first of all, we have been able to solve the numerator part for all these patterns. The numerator, we are going to solve the numerator. Now let's go to the denominator. Now at the denominator, what do you have? I have x is power 1 here, right? Which corresponds to the first derivative. Here I have x is power 2. This corresponds to the second derivative. Here I have x is power 3, which corresponds to what? The third. This is x is power 4. Which corresponds to the fourth derivative. This is x is power 5, and the denominator which corresponds to the fifth derivative. Then this is going to be what? X is power what? X is power n, which corresponds to the nth derivative. So it means that the nth derivative of y equals to ln x can be written generally as this. What did you say?
I'm agreeing with you.
All right. So you are being able to solve the n derivative of lim x. But it's going to get complex when you have product function, and you might not really be able to do this. But if you know the basics of this y equals to lim x, and I will talk about one other shape function. So let me see. Let me see again. Let me talk about, okay, it's not here. So let me talk about, let me erase. Can I erase this? I can erase this here.
Yes. Yes, you can.
Okay. So let me talk about sine. Share the about sine, of course. Now, so if I have, let's say if I have y, let's say y is equals to cos x, for example. I don't know if I should just use. Let me use sine x. So let's say y equals to sine x. I'll find the nth derivative of this guy. Now you agree with me that y prime, which is the first derivative, is what? Cos x.
Yes.
Then the second derivative is going to be, it's not y squared, it's just means second derivative. So I hope you understand. I'm just using that. Then the third, that should be minus cos x. Now the fourth, that's sin x. The fifth, cos x. So you can see that at this point, this one and this one, they are the same thing. This one and this one, they are the same thing. Yeah, you just keep moving in that pattern anyways. But that's not the essence of our generalization. But now, there's a way I can write this as a function of sin x. And this particular guy is the same thing as sine let me be careful what I'm to write next. I have to be careful what I'm to write next. So this one is the same as, first of all, the first original question is the same as sine x plus 2. Sorry. This first derivative is the same as sine x plus pi over 2. At the first derivative, your sine moves by 90 degrees. So just go to it. So remember that sine a plus b is equals to sine a cos b plus cos a sine b. If I open this bracket, I'm going to have sine x times cos pi over 2. And cos pi over 2 is cos 90. Cos 90 is 0. So 0 times sine x is 0. Plus cos x times sine pi over 2. Sine pi over 2 is 1. 1 times cos x is cos x, which gives you this guy back. Now, at the second derivative, your sine moves another pi over 2. So that will be sine x plus pi over 2 plus pi over 2. That's plus pi. At the third derivative, it moves by another pi over 2. Then I have sine x, sine x, sine x plus, so pi over, so pi, if I add pi over 2 to pi, I have 3 pi over 2. Also, at the fourth derivative, it moves another pi over 2. That will be sine x plus 2 pi at this point. And the next junction, it moves another pi over 2. That's sine x plus, in this case, I'm going to have 5 pi over 2. So, in general, what I have in essence is that this one makes this one. So, for the first derivative, I have x plus 1 pi over 2. At the second derivative, I have sine x plus 2 pi over 2, which is pi. At this junction, I have sine x plus 3 pi over 2. Here, I have x plus 4 pi over 2. That's at the fourth derivative. At the fifth derivative, I have x plus 5 pi over 2. So that means that my nth derivative is going to be sine x plus n pi over 2. So this is going to give me the n derivative of sine x in that regard, which is this. Do you understand? Yep.
Yes.
So this is very essential. This is very essential. Just know it by heart. You might maybe ask something like this in theory in the exam. We understand the basics. So let me just use this black whiteboard, normal whiteboard. So that's that. So now, let's talk about the Leibniz formula. The Leibniz formula, you have something like this. So if I have y to be u times v, u and v are both function of x. So my dny, that's the n derivative of y, is given as I think I still remember this, u times dnv plus, just like you are doing like it's kind of binomial kind of expansion, but this guy is derivative, du dn minus 1v. First of all, no, so there will be n combination 1 here.
Okay.
So this one is n combination 0, which is 1. It doesn't really count. N combination 0 is 1. Plus n combination 2. This one is going to be d square u. Then this one will be dn minus 2v. Do you remember this formula?
No.
dn minus 2v plus, until I've exhausted my, then this is going to have n combination n. So this is going to be dnu times, just as I get to b, or let me just put b times dnu. You can never exhaust b in this regard, but let's just write it this way. Now note, so this is called Leibniz formula. This Leibniz formula. Maybe I might not be right with this spelling of Leibniz, but Leibniz formula. I still remember all these things. I did it back then in 2011. I still wonder why I still remember all these things, because I just can't remember. So this is called Leibniz formula. Now note that your u here in this case, u should be something u should be something that whenever you differentiate, it's going to terminate. I won't have to write this. So u should be something like something you can differentiate that is going to terminate, while your v is something you're going to be able to find the general term, the general derivative of it. Something that's going to give you something like your dnv that you can find the general term too. Do you understand?
You have that used to be something.
So if I have something like
Sorry, I think. Hello.
s, hello, I can hear you.
I said at least can you come again from the U part? Like you should be something.
I said so u should be a function whereby if I should keep differentiating it, it should terminate at some point.
Okay.
Then your v should be something that you can find the general derivative of it. So for example, for an illustration, I give this. In this case, my u is going to be s squared, because if I should keep differentiating s squared, I'm going to get 0 at some point. And Linux is something I can find the general term. We already found the general term of Linux in the previous case. Do you understand?
Okay.
Yes. So now let's Pascalize this with one or two examples. I'm going to rub the board now. Can I rub the board?
Yes.
Okay. So I'm going to rub the board now. So now, let me look at the case study. Here I have like s squared cos x cos x. Let me take this case. X is power 4 in x. So I want to take two cases. X is power 4. X is power 4 in x. And say s squared sin x. Maybe this. I think x is power 4 in x is too big. I'll have to be. I'll waste much time. So let's say y is this guy. So you can see I can separate it into u and v. So my u is going to be x squared because I can easily keep differentiating it and it's going to terminate. And my v is going to be ln x. Now my du, what's my du? It's going to be 2x, right? My d square u, if I differentiate again, it's going to be 2, right?
Yeah.
If I differentiate again, it's giving 0, so it's a waste of time. So now the next thing I'm going to do is, what's my general term for ln x? So my dnv is going to be, I think as we already found out, minus 1 is power n minus 1 times n minus 1 factorial over what? X is power n. So in general, my n derivative for this function will be the ny is equals to, what's the starting point of my formula? U n combination 0 whatever. So is n combination 0 u times what? dnv, abi? So n combination 0 is 1, so that doesn't matter. So what's my u? X squared times dnv, which is this guy. So times minus 1 goes by n minus 1 times n minus 1 factorial all over x to the power n. So what's the next term? Plus n combination 1 abi du times dn minus 1 v, right?
Yes.
So that will be plus my n combination 1 is what? N combination 1 is what? N times du. My du is 2x, as you can see on the screen. Now dn minus 1v means n I just see n in my dnv, just put n minus 1. Do you understand?
Anyway, you see n.
In this general term, put n minus 1 instead. So that's going to give me minus 1. So n minus 1 here is going to change to n minus 2, abi? Times n minus 2 factorial all over what? Expressed by n minus 1, right?
Okay, yes.
Now, what's the next term again? I'm going to stop at the square u because that's where I could stop, because I cannot find the cube u because everything is 0 from there. So my next term is going to be n combination 2 to square u. Remember I did very well. The square u the n minus 2v, right? So I'll just write plus. What's going to give me n minus n combination 2? N combination 2 is the same as this. N times n minus 1 all over 2. I will explain. You understand? This n combination 2 times the square root is 2 times the n minus 2v is just like anywhere I see n here, put n minus 2 minus 1 raised by n minus 3 times n minus 3 factorial all over sorry all over x is by n minus 2d. Okay, let me ask, do you understand why n combination 2 is this?
I was going to ask.
Okay, now you remember that n combination 2 is the same thing as what? N factorial all over n minus 2 factorial times what? 2 factorial. Do you agree?
Yes.
Now, n factorial is still the same thing as n times n minus 1 times n minus 2 factorial. Do you agree?
Yes.
So, all over n minus 2, sorry, might be all over n minus 2 factorial times 2 factorial. 2 factorial seems to 2, right?
Yes.
So n minus 2 factorial cancels n minus 2 factorial. So I will have n times n minus 1 over 2. Do you understand? Okay. So what is now left is now to try and factorize this guy. So I'll make it simple. I know this is going to take a lot of our time, but then. So first of all, let me make this simple as possible. Now, I write minus 1 x power n minus 1 times n minus 1 factorial. I know you might be asking me that where is my x squared? So by bring this x squared down here, it becomes x power minus 2, right?
Yeah.
So x power minus 2 times x power n, that should give us x power n minus 2. Do you agree? Hmm? Hello, are you there?
Yes, I am.
Okay, plus n times 2 is 2n. Then times minus 1 is power n minus 2. Times n minus 2 factorial. Then the other is x up here. If it comes down to becomes x power minus 1. So x power minus 1 times x power n minus 1 is also x power n minus 2. Right?
Yeah.
Now plus these two, we cancel these two. Then I'm going to have n times n minus 1 times minus 1 x power n minus 3 times n minus 3 factorial all over x power n minus 2. Here we can see that the denominator is like kind of same thing.
Yeah.
But we cannot stop here. Yeah, we cannot stop here, obviously. So I wish this is a physical class. Maybe it could have been more convenient, like seriously more convenient. Where do you stay, calling me?
So I didn't hear you.
I said, maybe this is a physical class. It could have been more convenient, like seriously.
Yeah.
Where do you stay?
Oh, wow.
Oh, wow, that's quite fun. So now we cannot stop here. Now we have to factorize something out. So what do we factorize? Now you can factorize minus 1 is power anything. You can factorize n minus something out, like I think you just took up the light from here. But it's well, sure. But we should be able to finish this. Now, let me show this. It's, hold on, sorry. I think my system wants to go down. My system wants to go up now. Hold on. So sorry, let me just quickly finish up with this. Are you there?
Yes, I am.
Okay, so now I can factorize out minus 1 raised power n minus 3. Is that the one that is like kind of basic I can do? Because if you look at it, between n minus 1, n minus 2, n minus 3, it's n minus 3 that is kind of like the smallest, right? So now, if I say I want to factorize minus 1 raised power n minus 3, I can factorize that out. Also, out of n minus 1 factorial, n minus 2 factorial, n minus 3 factorial. So it is n minus 3 factorial that is like the smallest. So I can factorize that n minus 3 factorial. So let me factorize that minus 1 is by n minus 3 and n minus 3 factorial, for example, out of this. Also, the denominator, everything is common. I can factorize x is by n minus 2 out. Now, so what's going to be here? Now, if I factorize minus 1 is by n minus 3 out of minus 1 is by n minus 1, what do you think is going to be left? Minus 1
Raised power n minus
minus 1 is power 2. Add the power of this n minus 3 and 2. What do you have? N minus 1. Is that not what you have?
yes.
So that's why you have this. Now, if I should divide n minus 3 factorial by n minus 1 factorial, what do you think I'm going to have? Don't forget, this is what I want to do. I want to do n minus 1 factorial all over n minus 3 factorial. Now, what I'm going to have is, if you are thinking the way I'm thinking right now, I'm going to have n minus, sorry, I'm going to have, so let me erase this. So, I'm supposed to have n minus 2. So how am I writing this now? I'm going to have n minus 1 times n minus 2. Do you agree with me?
Yes.
Okay. Plus, where's my system? Why is this super slow?
Hello, I can't hear you.
Oh, sorry. I didn't know I was on mute. So if I do n minus 2 factorial all over n minus 3 factorial, what will be left is n minus 2, because I can do, so n minus 2 factorial is the same as n minus 2 times n minus 3 factorial. So that n minus 3 factorial will cancel n minus 3 factorial. I'll be left with n minus 2. Do you understand? So plus, I'll have n times n minus 1 as I have it here. So minus 1 is for n minus 3 divided by minus 1 is for n minus 3. That's 1. N minus 3 factorial divided by n minus 3 factorial. That's 1. So what I will have left is just this guy. Right? So what you just be left with is to what? Simplify this guy and multiply with this. So that will just be all. Do you understand?
Yes.
So I would like you to do this, complete this, and that's going to give you the end derivative for that particular problem. So tomorrow, sorry I have to end this class like this because my system just go up now, like now. So I want you to do this to find this end derivative of this particular question, x squared is power sine x. So I expect you to do this before tomorrow and just engage me on WhatsApp. Do you understand? All right, we are going to see tomorrow. Sorry, I had to end the class like this. Sorry, I had to end the class like this. I'm very sorry.
No problem.
All right, take care of yourself. Bye.
Bye.